Hello and welcome back to our Semiconductor Thermal Management series. Today, we'll be discussing thermal management in variable and flexible electronics, one of the fastest growing and most technically demanding areas in modern semiconductor design. From smartwatches to biosensors, heat must be controlled safely and efficiently in devices that come into direct contact with the human body. Let's explore how engineers are solving these unique challenges. This video will cover 16 key areas. We'll begin with the importance of thermal safety in variable electronics, then move into heat generation, substrate behavior, and material choices. Next, we'll imagine cooling strategies, both passive and active, as well as simulation techniques, circuit level design practices, and real world case studies. Finally, we'll look at future technologies like self cooling films and thermally smart fabrics. Unlike laptops or servers, wearable devices sit directly on human skin, meaning thermal management must account for comfort, safety, and biocompatibility. Shown here as a flexible wrist mounted patch and a system schematic of a wearable device, highlighting the layout of heat generating components. These devices are small, but their thermal challenges are anything but, making thermal design a top priority for engineers. Even modest heat buildup can cause discomfort, sensor drift, or failure. In the image here, we see how proximity to skin limits airflow and traps heat, especially under clothing. Unlike traditional electronics, wearables operate in insulated, sweat prone environments, increasing the importance of thermal safety thresholds in every aspect of the design. Flexible devices are built on thin film materials that conduct heat poorly. Shown here are thermal simulations of heat spreading across thin polymer sheets. With limited metal and constrained volume, heat accumulates quickly and spreads slowly, often building up in localized zones directly against the skin. Understanding this thermal behavior is the foundation of wearable system design. Heat in wearables comes from SoCs, wireless radios, biosensors, and LEDs. In this PCB image, we see power hungry components clustered tightly, particularly in smartwatches and earbuds. Data transmission, especially over LTE or Bluetooth, adds further thermal load. When placed against skin, even small chips can cause perceptible warmth if heat is not properly managed. Human skin can tolerate temperatures up to about 43 degrees Celsius before pain receptors activate, but to prevent irritation or burns, surface temperatures must be limited to under 41 degrees Celsius, as shown in the chart. Regulatory standards reinforce this limit, especially for medical and consumer variables. Designers must validate thermal behavior under worst case conditions, including summer heat, direct sunlight, and physical activity. Most flexible electronics use polyimide, PET, or PDMs, all with low thermal conductivity. In these thermal tests, we see heat localized in regions with active components, while adjacent zones remain cool. Substrate thickness, contact with the skin, and ambient temperature all affect how well heat flows and dissipates, making substrate choice a major thermal design factor. To enhance lateral heat dissipation, engineers integrate thin, flexible heat spreaders into wearables. The first example shows a graphene film layered into a smart patch, increasing surface area for heat to escape. The second uses a flexible copper foil bonded to the enclosure interior. These materials maintain device flexibility while improving thermal uniformity. Thermal interface materials, or also known as TIMs, must work on curved, uneven, and delicate surfaces. Shown here is a soft, gel like TIM conforming to a curved sensor. Other solutions include phase change films that activate during heat spikes. These materials must balance thermal conductivity, compressibility, and skin safety, making TIM selection especially critical in wearable applications. Passive cooling remains the first line of defense in wearables. Designs incorporate ventilation grooves, thermal vias, and heat spreading enclosures, as seen in the images here. With no room for fans or large sinks, every layer must contribute, from PCB layout to enclosure geometry. A well designed passive system reduces reliance on active cooling, preserving battery life and silence. Active cooling in variables is still emerging, but it is promising. Miniature Peltier elements, as shown here, can remove heat efficiently, though they require careful power management. Some prototypes use microblowers or thermoacoustic cooling in a thin, flexible form factor. These systems only engage under high thermal load, allowing most operation to remain silent and passive. Thermal simulations predict how heat moves through thin, flexible layers in contact with the body. Here we see a FEA, or also known as finite element model analysis, on a wrist mounted patch. Thermal testing then validates the model using IR cameras or embedded thermistors, often with a synthetic skin simulator, to replicate real world conditions. Beyond materials, thermal design happens at the circuit level. In this circuit, heat generating components are distributed across a larger area, minimizing local hotspots. Engineers also stagger power intensive operations to allow cooling time. By integrating temperature sensors, the system can adjust task timing to reduce heat output in real time. Now let's take a look at a couple case studies. Our first case study focuses on a flexible biosensor patch. Using a graphite film bonded on PDMS, engineers reduced surface temperature by 5 degrees Celsius, improving skin safety and sensor accuracy. In the second case, a smartwatch SoC used a copper foil and TIM under the casing, keeping the temperature under 40 degrees Celsius even during LTE data bursts. These examples show how simple materials, when applied wisely, can significantly improve thermal performance. Looking ahead, thermally conductive textiles and self cooling coatings are changing the game. In the first image, fabric with conductive yarns actively spreads heat. On the right, we see a film using phase change or diode like behavior to regulate temperature. Together with AI controlled thermal feedback, these technologies will enable variables that stay cool, smart, and safe, no matter the environment. Thank you for watching.